There we go. So, of course, we were finishing up talking about objects, right? And what we did here was create a simple, at the beginning, a very basic class, a simple class, the friend class, that just held some information. You know, it had a constructor, some fields, getters and setters, and a toString method. I think that was about, oh, we wrote an equals method as well. But we did know that the equals method we wrote was kind of a, not a completely correct one. There's a better way to do it, and you can actually see the aside here for more details on how to make a better equals. But just a note, another aside I have down here with the toString for the friends. So what we've done is, did I explain this last time? I think we did. Contact list. Yeah, okay. Yeah, we did. So we start with the empty string, we loop through all the friends, and we just actually just concatenate the string, the current string, which starts as an empty, with the string version of friends at index I. So friends at index 0. And then we take that and append or concatenate with friends at index 1. And then we take all of that and concatenate with friends at index 2, and so on and so on and so on. And then we return S, which is the built string. So this is like string building. Now, realistically, if you do it like this in this class, it's fine. You're doing fine. It doesn't really matter so much. But realistically, this isn't a good way of doing a toString. Really, what you would want to do is something called a string builder. And there's an aside here on string builder. This one's a very simple one. They're more efficient to work with as far as your computer is concerned. So you'll notice some might even argue it's easier to work with, is you just start with a new string builder, and then you just say builder append whatever you want to append. So say I append the string version of friends I, and then a new line. Friends I, new line. Friends I, new line. And then once I'm done, I just tell the builder to toString, and I return that one string. I won't go into the details right now. This is just me showing you what this means. But yeah, this right here is actually a bug in the type setting. So if someone wants to get fancy, they can make a GitHub issue related to this typesetting issue in topic 3 aside on builder. All right, I am recording. Okay, good. Okie dokie. So the objects reviewed. Now on to collections. All right. So what we're going to talk about is collections, abstract data types, data structures, implementations, and then the big one, abstraction. So collections and ADTs, abstract data types. A collection is a word we use to mean a group of things. That shouldn't be group of things, although I kind of like it as group of things. But there is another GitHub issue someone can create and get all of their contributions on the GitHub, on the course, recorded in time. A collection, or it's a group of things we want to kind of treat as some conceptual object, like a contact list or a course list or a stamp collection, whatever. Like, it's a collection of things we want to kind of treat as a unit in some way. And you can think of the contact list as a good example because it's just a collection of friends, right? So what is a contact list? Well, it's a collection of friends, but we interact with the collection of friends in certain ways than we do if we're interacting with individual friends. See, for example, the methods for friends versus the methods for the contact list itself. In computer science, we have a few very popular elementary collections. And I'm not saying elementary as like, oh, basic. I'm using the word elementary as like they are like core, base, important ones, right? Stacks, queues, lists, trees, graphs. I mean, this list does go on. In fact, I should probably change this to bag because we will be talking about bag specifically later. But yeah, this list is far from complete, but they will be a big part of your early computer science courses. Fundamentals. So, linear collections. We're going to start learning about linear collections, but a linear collection are those where the data is arranged by default in some sequential way. Each thing has a predecessor and a successor, except for the ends, of course. But like, think of the list in Python. If you go to the beginning of that list and I ask you, well, what comes next? You go, well, the next thing. There's no ambiguity to that question. That question has a simple answer. And these are linear collections. I can take the data and just kind of like draw a line to connect them. The first linear collection we're going to jump into in the course is a stack. So if you've ever been to a buffet where you have like a stack of plates, when someone comes along and puts plates on that stack, where do they put them? Well, they put them on the top of the stack. And then if you come along and you want to take something off the stack, well, you take them off the top of the stack. With a stack, all of the action happens at one end, at the top. No one's making any insertions in the middle. All of the action is intended to be at the top. You add things to the top and you remove things from the top. I'm hearing boops. Yes, Control Z is exactly an example of a stack. So adding and removing data from a stack happens from one end. The last thing we add to the stack will be the first thing off. So every time I make a change to a document, I'm adding that to a stack. If I want to undo it, I Control Z it, undo. That top thing added gets removed from the stack. Similar to like if I hit back on my website, right? I would pop this page off the stack. It's like you're walking deeper into a jungle and then you have to run back. Sure, yeah. But then you gotta, once you start running halfway back, you gotta turn around and go deeper into the jungle. So then you start adding to the stack again. Q. You've all been in a line before. I know you've all lined up for something before. Some of you may have even lined up for something today, like Starbucks coffee. I don't know. But a queue is just a line. Adding to the queue happens at one end, and removing happens at the other end. So where this right here, the last thing added is the first thing to get removed. Here, the last thing added would be the last thing to be removed if nothing else was added. So with the stack, all of the action happens at one end, where a queue, the action's happening at both ends, but it's always only ever inserting at one end and removing from the other. Adding to a list happens at one end, and removing happens the other. The first thing that gets added would be the first thing to remove. Okay. What? Same, like the undo thing? Yeah, it's an example of queue would be an assembly line. Yeah, sure. Like literally anything like that has like a first come, first serve basis is a queue. And then we have lists, right? Adding and removing from a list will depend on the type of list we have. In the above example, this is what I would call an ordered list, right? Where if I wanted to add the number 58, well, to say, oh, it always adds at one end versus the other end doesn't work here. Really what it is, well, if I add 58, I want to make sure that it's added in the correct spot. So I could say, okay, is 58 less than 16? No. All right, so I know it must come after 16. Is it less than 23? No, it's got to come after 23. Less than 29? Must come after 29. Less than 40? No, must be less than 51? No. So 58 must come after 51. Less than 67? Yes. Oh, so it must come before 67. And I just concluded that it has to come after 51. Therefore, it must go right there. So Python lists are a very general type of list, and they are in fact also a generalization of a stack and a queue. You can do more with it, but you could treat a list like a stack or a queue in Python. But these are our linear collections, right? Like I can draw a line. You know, there's a line here, and you know, a list. There's a line. There's straight lines. T2. It'll depend on how this is created. If you start with an empty one, you could just make sure every time you add something, you add it in the proper spot, right? So it's kind of like you're doing an insertion sort, but that's a later issue. Good question, though. Now, we also have non-linear collections. And with these, sometimes there's no natural way to arrange our data in a nice sequential way. Here's another issue. This is grammatically incorrect. Someone could make a killing on making issues today. Even better, someone can make a killing on making pull requests to address these issues. So there's no way to arrange our data in a nice sequential way. And sometimes there maybe are many successors, and sometimes there might be many predecessors. Sometimes the idea of a successor doesn't even make sense. So we can talk about a tree, and here's our tree. We call this the root, and these are the leaves of the tree. I know it's upside down, but it is what it is. So we have a root. And if I ask you, like, okay, what comes after root directory? Right? What's next? You're going to go, well, Because with a list, if I'm at 29 and I say, what comes next? You're like, oh, it's 40. What comes after root directory? Ooh, I mean, we've got 3 options, right? It's not a natural question to have an easy answer to. And I might say, what do I say? The data is arranged in a hierarchical way with a tree. Like we got root directory, documents, and settings. So like there's like a hierarchy. Every element has at most one parent with a tree. So I say at most one parent. Everybody can only ever have one parent node, except the root, which will have no parents. Every element has at most one parent, but potentially many children. Yep, so root directory has 3 children, 1 child, 2 child, 3 child. This is jargon I'm using for the trees that we're going to talk about starting in topic 21. So this isn't critical that you're following along with the jargon right now, but I'm using it for correctness. Then if I ask, okay, what comes after program files in the example? There's no obvious answer. Is Microsoft Office, Adobe? I don't know. And we can think of trees as actually a generalization of a list, which is weird, but it totally is. And we're going to hit this way more later in the course. Because if I show you this as a list, and then I say, oh, a tree is a generalization of that, you're going to say, wait, this really looks nothing like this. But realistically, I could just say, okay, make a tree where everyone has at most one parent, but actually in our specific tree we're making only has 1 child each. Well, that would actually be a list, but we'll talk about this generalization later. Kind of. Depending on how you implement it, you could totally think of it that way. I'd be careful trying to find like a rule of thumb here, but yeah, you could totally make that argument, Obi-Wan. And then graphs. A graph is actually a generalization of a tree. So the idea is, with a graph, like there's not necessarily any hierarchy here, right? And there's no constraints on like a parent can only have one, or a node can only have one parent, and a parent can have many children. Well, here you can have as many connections as you want, and the idea of parents and children stops to make sense. But a graph could be used to kind of represent entities that have some form of relationships. So in this example, I've got like some cities, right? And they represent their airports. And at any given time, maybe this is the flights that are available. From Toronto, I can take a direct flight to Moncton and Halifax, but apparently not to New York City. But if I want to get to Buffalo from Toronto, I could go Toronto to Moncton to Buffalo, or Toronto to Halifax to Buffalo. There's options. This shows all of like the pathways here. So the data is represented along with relationships to one another. So we call these vertices or nodes. An individual is a vertex. And then these are what we call edges. The thing that's connect them, we call them edges. This is a graph, and it's a generalization of a tree. We won't be sinking our teeth into graphs in this course. There's no goal of explicitly learning graphs. That's a next semester thing or next year thing. But they are a generalization of a tree. In linear lists, we have an index, but in a tree, how do we know the position of the index? Does it see? You raise a good question. That's what makes this whole nonlinear thing. It's like, well, what comes after? What comes after? Well, that question kind of is hard. Like, it doesn't really make sense, right? Reminds me of the 4-color theorem in a way. I don't know. No, Count Dooku, you are absolutely correct. The 4-color problem is a problem on graphs. You may not have seen the 4-color problem represented as a graph before, but it's commonly described and presented with these graphs. But T2, there is the idea of indices doesn't really make sense anymore, asterisk. So that's kind of the issue with the nonlinearness. And then abstraction. Excuse me. So the big idea with problem solving is abstraction. You do this a lot in everyday life. You try to separate the what from the how. You know, I am communicating to you through my computer. I've got a webcam there. I've got a mic there. You know, I'm making the recording. I've got my keyboard. I've got all my setup. This is how I'm like interfacing with you. But that's the level of abstraction that I'm working with. I'm working with this interface. How this interface goes and enables me to be giving you a lecture right now, I have no idea. There's so much going on, but that doesn't matter to me because I am working at this level of abstraction. I'm working with my interface. I don't need to know how I am connecting to you, all of you at the same time and everything. That doesn't matter to me right now. What matters to me is my interface and how I interact with it. If I had to deal with all the stuff under the hood, I'd lose my mind. If I had to, I wouldn't be doing this right now, you know? So I deal with a certain level of abstraction that I'm comfortable and happy to work with. It's exactly like the car parts analogy. We all know how to use our cars, but if I asked you to take your car apart and put it back together and have it work, you're not going to do that, are you? You'd be a business major if I had to deal with all the underneath stuff. What? Maybe with help of Donut Media. I don't know what that is. But anyways. So the abstraction. We try to separate the what from the how. What can we do versus how it's actually done. What can I do with my car? I can get in it and I can drive places. How does it actually do that? I don't give a shit. I just want to be able to use it. Obviously, we care about what's under the hood. That's a big part of this course. We're going to learn about stacks, and we're going to deal with stacks at a level of abstraction. We're going to write the code to make stacks, so there is the what's under the hood. But it's about separating the what from the how. So no, we know what we have to do to drive a car, but we don't need to know how the car does what it does. We know that we wanted to append things to a list in Python. You didn't need to know how Python actually, the Python lists did that though. It didn't matter to you because you interfaced with the lists at the level of the methods that were available to you for those lists. You could say my list dot append. Boom, there, you appended to it. But how did it do that? Don't worry about it, right? So that's the abstraction. So the above ADTs, abstract data types, are all just the what. Okay, we're going to talk about the what's a lot. This is what a stack is. You add things to the top, you remove things from the top. This is what a queue is. You add things to the end, you remove things from the other end. This is what a list is. This is what a tree is. I'm explaining you what they are, but I didn't tell you how you would go implement those things yet. But you don't need to know the implementation. If I gave you the code for a stack and told you, okay, you can push and pop things off the stack. That's the jargon we use for interacting with a stack. You could do it without needing to know how it worked under the hood. You can all use a Python list without needing to know how it worked under the hood. So the ADTs, we could just add and remove stuff to a list. This is how we interface with the thing. At no point do we talk about how or implement the ADTs. Or implement these ADTs actually do their thing. At no point do we talk about how these ADTs or implement the things actually do their things. Here's another grammatical issue. Man, someone is going to crush it on the GitHub things today. In fact, maybe there are multiple options for how for a given what. For example, how do you want to build your stack? Well, there's a lot of ways we can do that. How do you want to build your tree? There's a lot of ways we can do that. What? Instead of comp sci, hey now, thought I was having what? I'm very confused as to the jokes you're making, but maybe I'm too old. All right, layering. If our systems are large, we may start to have multiple levels or layers of abstraction. If this is the case, we may want to group our components and restrict how some layers of abstraction interact. In real life, we play this layers games all the time. Tell me how to cook pasta. Okay, boil salted water and add pasta. Wait 10 minutes. Then I say, tell me more detail. Well, you can do this again. You can say, okay, well, fine. Get a pot, fill it with water, put it on the stove, and blah, 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 blah. So there's layers here. And we can think about the layers of abstraction even in the collection we wrote about the contact list. We have our friends. That's one layer of abstraction. That's our representation of a friend. And we can interact with friend objects. But then we had another layer. We had that contact list layer, which is, okay, well, here's how we interact with a collection of friends. So we're like multiple degrees removed from the friends, but that's fine because we like this layer of abstraction. Because if you had to deal with everything at the top level, having to go all the way down to how the neurons start to fire, muscles contract and everything, ion pumps, and it's not going to happen. The point is, it's, turtles all the way down, but that's, we have layers of abstraction and we interface and deal with stuff with abstraction to keep our heads on. Otherwise, we're going to lose our minds because there's just too much detail. If I want to make pasta for dinner, I don't care. And I don't want to care about ion pumps, okay? I just want to go boil some salted water and add some pasta and come back in 10 minutes, right? Okay, data structures. So a data structure is an actual implementation of an abstract data type or a collection, okay? So using the contact list example, the what would be, we keep track of friends, we can add and remove friends, we can get a friend. That's the what, the functionality it has. The how is like the actual code that describes what it's doing. So if I go here and I go back to lecture 1 and I say like, okay, my friends dot, okay, I can add, get, toString, clear friends, remove, get, index of, get size, update email. I have all these things here. This is the what I can do. But when I'm looking at when I'm looking to interact with my contact list in my main method here, I'm looking to interact with it based on what I can do with it. And if I say get size, okay, great. But I don't need to know how this works in order to use it here. I need to know what it does. Well, this returns the size. But I don't need to know how it does what it does. If I go and look at contact list and I look at, where's size? I think it's near the top. No, where is it? toString. Get size. Well, here's how it does it. It's a simple one. Add. Here's how it does it. Add. Oh, interestingly enough, though, this has expand capacity, which is a private method. So all of this right here is needed for the add method. This is the how it works. The code describing how the functionality does what it does is the how. But as far as I'm concerned here, when I say add, I don't care that, maybe I had to expand capacity. I don't care if I had to go, do all this. All that mattered was that I could add and it worked. That's what mattered. Is there a way you could count the objects in the list instead of increment the counting size? Yeah, you totally could do that, but it's actually just easier to increment the count size. But you totally could do it that way. Point being, that's another how. As far as I'm concerned, when I say get size, when I say this, maybe it is going through and counting it. Or maybe it's just returning some field size. Do I care though? No, I don't care. I just want to get the size. That's what I care about. I care about what I can do with it. I don't care how it happens. I just need it to happen. All right? If I'm a boss and tell you, go solve this problem, and then you come back and you're like, I solved it. I go, great. I don't care how you did it. I'm just glad that you did it. There, abstraction. That's not a great example, but whatever. Okay, and the how would be the actual code. A large focus of the class will be both on the what and how, and a big part here, and listen carefully, because this was something that I remember when I took the equivalent of this course. This was something that was not emphasized well for me and caused me a lot of confusion. But a big focus is the what and the how, and how we can keep them separate. That is a big thing here. The interface and the implementation. The what from the how. Note, I'm going to give you a warning here. It's not uncommon. So I was like, oh, okay, collection and abstract data types are the what's. They're like, oh, stacks, lists, queues, trees, graphs. And then the data structure is an actual implementation. A data structure is a how. I'm going to warn you, it's not uncommon for people to use data structure or ADT kind of as a catch-all to mean both ADTs and specific implementations. Yeah, I probably will do that myself a number of times through the course. The point I'm making is it's not going to be critical that you're like, on no point is there going to be a question on the exam that says, what's the difference between a collection and a data structure? No, that's not important. So much so that people mix these two up all the time. Explain about what? I'm still a bit confused about it. Can you explain? Can I explain what? Sorry. I'm not sure what you're asking. Oh, okay. All right. My goodness. All right, next topic. Let's close this. The stack. The stack is our first data structure that we're going to be playing with. Oh, pardon me. ADT. It's the first ADT we're going to be playing with. See, I just did it, and that was not on purpose. Okay. Right now, we are defining a stack. If you start to ask the question, well, why would you do it? Like, why would you want to do that? You're kind of going about this the wrong way. At this point, we are inventing a stack. So everything we say is the way it is. We are gods. We are defining what it means to be a stack. ADT, abstract data type. So stacks are a collection of elements that are only added and removed from one end. Like your collection of plates at a buffet. Every time you want to take a plate off, you take it off the top. You don't start trying to grab it from the bottom. That's a recipe for disaster. Every time you have plates that you, like a clean plate you want to put back on the stack, you add it to the top. Again, trying to put it in the middle, it's asking for disaster. You probably have a stack of plates in your cupboard right now at home. So given this, people will use the word, or people will say last thing in will be the first thing out. It's LIFO, last in, first out. The last thing that gets added would be the first thing out. If I just clean a plate, put it back on top of the stack, your roommate comes along and wants to eat something, they'll take the plate off the top of the stack, assuming it's clean enough. Does the stack collection, like it depends. Are collections and ADTs, yeah, you can say that. But again, don't worry too much about these semantics. Okay, stack of plates that you'll eat, see at a buffet. Web page history and the back button. Undo in your text editor. The call stack, which a call stack is something that your computer uses for managing running things. And we will learn a little bit about that far later in the course, but it is, in fact, a stack. So, let's say I want to add something to a stack. Well, visually, this is what we've got. We've got our bottom of the stack. Let me go here. We have our bottom of the stack, and this is the current top of the stack, this white plate. Now, if I come along and add this turquoise plate, like there, well, now it's the new top. The thing that was the top is now not the top anymore. And the bottom, I mean, the bottom's left alone. Everything else is left alone. All we did is just add something to the top. And then if we want to remove something from the stack, well, we have our top, we have our bottom. We just take the thing that, like, we just take the top thing off, okay? And now the thing that was under the thing that was at the top is now the new top, right? If I take the top plate off the stack of plates, the plate left on top now is now the new top, because that's how our universe works. So, and again, the bottom, like everything else is left unchanged. It's just all the actions happening at the top. You can have a stack of exams. You know, I take the thing off the top, I can put it back on. If I take one off the top, well, the new top is the new top. Stack operations. So, okay, any questions about a stack? Again, don't ask deep questions yet, because I've only introduced the idea. But if you have any questions about anything we talked about yet, definitely ask. Okay, Type away if you haven't. Okay, stack operations. So on a lot of collections, we're going to be looking at, our stacks, our queues, our bags, our trees, we're going to want a way to add something to that collection, to that ADT, remove something from the collection, and maybe look at something but not remove it. These are three common things we're going to want to be able to do with our collections. We want to be able to add stuff to it and take things out of it. Like our contact list, we want to add friends, remove friends. In the assignment, we want to add countries, remove countries. In the lab, we want to add courses, remove courses, right? However, these are going to be done in different ways depending on the collection. Because again, add. How do you add something to a collection? Well, is it a stack? If you do, it all happens at the top. If it's a queue, well, it goes to the end. This is going to depend on what the collection is. But there are going to be a couple of other general things that we're probably going to want for our collection. One is empty. It's just going to answer the question, is it the case that nothing is in this collection at this point? Do I have an empty stack? Do I have no friends in my friends list? Do I have no countries in my country catalog? Size, which is just a way to tell me how many things there are in the collection. So if size is equal to 0, what do you think is empty is? Test. If size is 0, is empty should be true. Well done. Boolean, well, it's type. And then, of course, our toString. We like toStrings. Tostrings are great for getting a string version of our object, so we like it. Okay. These are the three words we're going to use for adding something, removing something, and just looking at something. For our stacks, all we can do is push things onto the stack. That means add something to the top. So our adds are push. Push, add. Pop it off. You remove something. But the pop always happens from the top. And then peek is look at the thing at the top, but don't remove it. Just have a look at it. Is it clean? I don't know, right? Why is pop instead of pull? Pop and pull? Push, pull? Well, because you don't pull. I guess you could pull. I don't know. No, we like to pop things because popping's more fun. Yeah, push and pull because pop is cooler. I agree, Obi-Wan. And then peek, yeah. So push, pop, peek. And then we'll have our isEmpty, size, and toString. It is against, based on this is all we're going to do. Push, pop, peek. That's it. It is against the definition of what we just said. It's against the definition of a stack to access anything from anywhere other than the top. Peek is when you're sus. Peek isn't sus. You use peek when you are sus of something, right? So pop, peek, push, pop, and peek. That's what it is. You're not allowed to access anything from anywhere else. That's the rule. We might say like, well, I guess the exception kind of is the toString because you want to print out the string, like you want to get a string version of the stack. So you could think of it as like, well, you're getting the string of things that are at the top. It's the whole thing. But that's, you're making a stretch. Really, all the actions at the top. That's it. The stack abstract data type. With this, we know what the operators are and how they are used. We can push things on the stack, pop things off a stack, and we can peek. If I gave you a physical stack of plates in real life, and I'm not saying like, it's analogous to the computer. No, it's the same thing. It's just a stack. If I gave you a stack of plates in real life, and I said, okay, push this new plate onto the stack, you know what that means. Pop the plate off the stack, you know what that means. Peek at the stack, you know what that means. And then if I asked you like, okay, is it empty? Well, you can answer that. And what's the size? Okay, you count or something. You all know what it is and how it works. No. You all know what it is and what you can do with it. You don't know how it works. So you know the what. With this, we know what the operators are and how they're used. But notice that none of the above explains a single thing about how the stack is implemented. We have no line of code anywhere that describes anything about how the stack works. Nothing about how the operators do what they do. Also notice that the above description has nothing to do with Java. Not a single thing. It has nothing to do with Java. It has nothing to do with Python. It has nothing to do with C++. It has nothing to do with so on and so on and so on and so on and so on. It has nothing to do with any of these programming languages. It has to do with the stack. It has, like, it could be a stack of plates, a literal physical stack of plates. It has nothing to do with these programming languages. Is this for only Java or is it also for Python? I mean, push, pop, peek. Oh, those terms are universal. They have nothing to do with any programming language. Push, pop, and peek, they are universally applied to stacks. You can pick up a textbook that doesn't even mention programming languages. In fact, if I don't have it here, it's in my office. I could take the textbook, Algorithms, third. I think there's a 4th edition now. But this book, this is a very important computer science textbook. This is a textbook one might buy. This is a textbook that talks about algorithms. And inside here, you will see, it's probably really hard to see because it's hard for me to see even. Look, data structures. Elementary data structure starts on page 232, and it'll talk about stacks and queues. If I go to page 232, it's going to talk about pushing, peeking, and popping, but you will not see a single line of Java code in there, or Python code, or anything. This has nothing to do with any programming language. It's just the definition of a stack. So examples where stacks might be used. Well, here's a pretty cool one. We'll use a stack to solve a problem without having to know how it's implemented. We can even write the pseudocode for an algorithm using a stack. Pseudocode is just a fancy word to mean instructions that kind of look like an algorithm, but it's totally not like code. You could make an argument that a well-written recipe is pseudocode. So a stack can be used for maze solving. And this will be your assignment too. It's easy to find a path through a maze with a simple depth-first search algorithm. The high-level idea is very simple. Pick a path you have not visited yet. Keep going until you find the end or hit a dead end. If you hit a dead end, you're done. Or pardon me, if you hit the end, you're done. If you hit a dead end, backtrack until you can find another path you haven't visited yet. Repeat. The backtracking is very easily handled by a stack. Think of like websites. Click, 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 back, 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 click, click, back, click, click, back, back, back. That's the idea. Bandersnatch. What? I don't know what that means. Bandersnatch. I still don't know what that means. I'll assume that's some. Okay. So, pseudocode for traversing a maze. Add the start of the maze to the stack. While the stack is not empty, get the top of the stack with a peak. If the top is the end, you're done. If there's an unvisited neighbor of the current cell, push that neighbor onto the stack. If there is no admissible neighbor, though, pop from the stack. That's basically it. So here's the idea. I'm going to click this to see if it'll... Okay. Push. Add that dead end, backtrack. Push, 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 pop, 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 push, pop, push, 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 push. Oh, we're done. There. Push, 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 dead end, pop, push, 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 dead end, pop, pop, and so on, right? How does it decide whether to go left or right? It'll be depending on the algorithm, right? So if it says, oh, pick a neighbor, well, you're probably gonna have a systematic way of going like, well, start at 12 o'clock and go clockwise or something. In fact, I'm pretty sure that's what I do. Go up first. So the priority is up, right, left. No, up, right, down, left. But it's arbitrary. So this will be very similar to assignment 2, yes. Okay, so try to see where the push, pops, and peaks operations are happening. All right, well, I ruined that for you. Again, notice that we are able to use the idea of a stack to solve this problem, the maze, despite not knowing how it's implemented. Again, Nothing about what we just said is how the stack peaks, how it pops, how it pushes. Doesn't matter. We don't even know anything about the underlying way the data is stored. We don't know anything about this data structure. We just know what we can do with it. So what we're going to do is we'll talk about the interface for the stack. There are many possible ways one could implement a stack. In fact, there's an infinite number. But every single implementation of a stack must be a stack, meaning it must push, pop, peak, is empty, toString, size. Okay? So if something is going to be a stack, because there's literally an infinite number of ways I could write a stack. A lot are going to be trash, but they could be, by definition, stacks. So we need a way to say, okay, this is a stack, prove it. Because if we can write a stack that is guaranteed to be a stack, then we know it's a stack. So in Java, we do these things called interfaces. And an interface, I think I heard a boop. We best not have to draw a maze with code like tic-tac-toe board on assignment 3. Don't worry, you won't actually. No. I will give you the code. I provide the code to do the printing. All you have to do is say print, and it'll play it all out, print it all out. Yes, thank you. You're welcome. You say something unpopular when you just hear boop, 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 boop. All right, cool. So in Java, we create an interface. We write an interface that defines what the operations of the stack are, but we do not implement a single thing. So we say, oh, we'll have the method push, we'll have the method pop, we'll have the method peak, int, or toString, size, is empty. You'll have all those things. But I'm not going to tell you how any of it happens. But then, when someone comes along and wants to implement their stack, they're like, I have a great way to code a stack. I have a great way how to make it do its how. What they'll do is they will implement that interface. And if their code correctly implements the definition of a stack, then they have a stack. Okay, so the interface will simply be a list of abstract methods. This is perhaps jargon, but it's a key word in Java as well. But abstract is the abstract thing. Abstract is the what, not the how. When we have an abstract method, it tells us what, it does not tell us how. Abstract methods are the method signatures headers, no actual body. Our method would be public. So public int some method int a int b semicolon. This is an example of an abstract method. There is no code in that method. It's just the definition of what it is. There's a method, it's going to return an integer, it's called some method, and it needs to take 2 integers. Constants will be static final. So here's an example of a stack interface. That's literally it. Public interface stack, we'll come back to this in a moment. Public interface stack, open squiggle, void push t element. So we have push, we have pop, peak, boolean is empty, int size. These are just the definitions of what we can do. Now, this T thing here is a new idea. The interface, is interface the return type? No. T is the type. So, you are probably wondering what T is. You're right. I think the best way to explain generics is through an example. Imagine you want to have a stack of type integer. Then you'd have to make something like this. You'd have to make an interface that says, okay, public void push some integer element, public integer pop, the return type pop. Then we need like a public integer peek and all those things. All of them written for integer. And then next thing you know, you also want to have a stack for strings. Okay, so you have to write another interface where you say, okay, public void push string element. Pop is going to return a string now. And now you want a stack of friends. Okay, so I need another interface that says push friend objects. And then pop, it's going to return a friend. There has to be a better way. Well, there is. The T is a stand-in for a specific type that can be specified later. It's basically a variable for a type. This right here, I had a really hard time with generics until I saw an example and I go, oh, that's cool. So, for example, if I use the original interface, this one, T, I can write this here, stack, and then I put in these like in the less than and the greater than like triangle brackets, the type I want. So now T would mean integer. So I have an integer stack, a new array of integers. There. Now, this right now, it's going to work with all integers. Oh, now I want a stack of strings. Okay, I put strings in there. Friends, I put friends in there. So T is a way to have a variable for a type, which is pretty cool. No, it wouldn't, because a list, we have other things we can do with it. A stack, all we can do is push and pop. Do you always say array stack? No. Who said array stack? Huh? Like in the code. Oh, I see here. That. Okay, good observation. I made something that is of what type? It's a stack. What do I have? I have a variable, my integer, that's a reference to a stack. But then I went and made an array stack object. Array stack is a specific implementation. It is one of the possible hows. In the above example, we're creating 3 stacks, each with a different type. We've gotten a little ahead of ourselves, but the takeaway is we can create an instance of a stack. We specify the type we want and the to mean the brackets. Okay. We will talk a little bit more about the next topic. We do not actually need to include the type on the instantiation, by the way, as a next thing. So anyways, there's some stuff for next time. You can look at the stack interface if you want. Where do I don't have it here. But anyways, that's that. I hear a bunch of boops. So, do you always array stack? Hey. And stack just confirmed is off the top. What? Yes. Okay. Could you do a linear search just popping until you find what you need? Yeah. And then you could put the things back if you want. Can you have a non-array stack? Absolutely. You can. There's literally an infinite number of ways you can have stacks.